it's important that we can interpret various motion graphs, acceleration time, velocity time and displacement time. And often a large part of this is looking at how they are grouped together, what is the links between them. I'm going to go through this in two ways. And first of all, I'm going to start with a fairly standard set of graphs with the acceleration time graph first of all. And what this first graph shows us is that the acceleration is constant for all the values of time. It doesn't change. So flat graph across means that that value is remaining constant. So this is constant acceleration. And then once we know that, that gives us some idea about what's going on with the velocity time graph. If the acceleration is constant, well, that means that the velocity is increasing by a fixed amount every second. That's what acceleration means. It doesn't tell us what the velocity starts at, so I've deliberately picked this graph. So it doesn't necessarily start at 0, it could. But then what we have is it's increasing at constant value in each second in the velocity time graph. And that gives us these diagonal sloping lines. So constant acceleration there, increasing velocity. And then lastly, if the velocity is increasing, well, velocity tells us how the displacement is changing per second. A velocity of 3 meters per second means the displacement is changing by 3 meters every second. And so if, for example, this started at 1 meter per second, then in the first second the object would cover 1 meter. If it then went up to 2 meters per second, in the next second it would cover 2 meters on top of the one that's already covered, and then the next second it would cover 3 meters on top of that, and so on. And what that gives you is this curve here, where the displacement is increasing, but in a curve because it's getting a larger increase every time. So increasing displacement but in this curved shape. So that's one way of looking at it. Starting from acceleration, you can work out what's going on with velocity, you can work out what's going on with displacement. You may also remember that the displacement can be worked out as the area under the velocity time graph. So that's another link between this graph and that graph. Displacement is area under a velocity time graph. If we look at it now the other way, and I've just taken the same graphs, but we're analysing them the other way round, i.e. starting from the displacement, what does that tell us about the velocity, and what does that tell us about the acceleration? And basically, if we look at the displacement, well, the velocity is the rate of change of displacement, the displacement per second. And basically that's a gradient, because the x-axis in all these graphs is time, then the rate of change of something is the gradient of the graph. So really what we can look at and see is the idea that here the velocity is small to start with. If I looked at that point, for instance, the gradient's got steeper. If I looked at that point, the gradient's got steeper still. Not terribly well drawn, but you get the idea. Even steeper. So if I took each of these points and worked out the gradient, that would tell me what the velocity is doing. And you can see the gradient is increasing, so the velocity must be increasing. So the velocity value is the gradient of the displacement time graph. And then we can do the exact same idea to think about the acceleration time graph compared to the velocity time graph. So the gradient of this velocity time graph is a fixed gradient. So the gradient at that point is the same as the gradient at that point, same as the gradient at that point, and so on. So the acceleration values are constant at all points. So the acceleration value is the gradient of the velocity time graph. And in this particular case, which is quite a common situation, single constant acceleration is what it gives you. Now in these graphs we're going to look at similar sort of idea, but we're going to include the kind of more real world type situations and also include the idea that it can change direction. So that's another kind of step up. And once again, if I just did the exact same reasoning as I did a second ago, if I looked at the gradient of this velocity time graph, then it shows me it's constant and negative there, it's constant and negative there, it's constant and negative there. All of those values, all of those acceleration values have a negative value. And this situation is the idea of throwing a ball straight up. Assuming there's no air resistance, then what you get is a constant acceleration of minus 9.8 meters per second squared. Now that often causes a bit of confusion. On the way up, right, the velocity is positive. So usually our standard convention is up is positive. That's kind of referring to the going up. Velocity is positive. Acceleration is negative. And because these are both acting against each other, i.e. the ball slows down. The value of the velocity is getting closer to zero. It's positive, it's decreasing, it's getting closer to zero. Zero is the point where it changes from positive to negative, i.e. when it changes from going up to going down, i.e. 0 is the greatest height. Okay, it's that idea of instantaneously stopping. It doesn't stay there at that point, but it's got to change between a positive and a negative velocity. It's got to pass through 0. That instant is its greatest height. On the way down now, if we look at this bit, the velocity values are now negative. The acceleration due to gravity is still negative 9.8. But because these are both acting in the same direction, i.e. the ball speeds up, and in this case in a negative direction, i.e. down. So we need to move away from the idea that we met in that 5 that a line sloping down always means deceleration. You've got to look in a bit more detail and say, is the value positive or negative? Is the line sloping up or sloping down? So if the value of the velocity is positive and the line is sloping up, then the object will accelerate. That's just like that 5. But if the value of the velocity was positive, for instance, and the gradient was negative, then the ball is going to be slowing down. When we go to the negative idea, if the value of the velocity is negative and the acceleration is negative, i.e. the line is sloping down, then you're looking at a ball that's speeding up in a negative direction. And lastly, if the velocity is negative but the acceleration is positive, i.e. the line is sloping up, then you're looking at a ball that's slowing down in a negative direction. In this last example, we're studying the motion of a ball which has been dropped and then bounces. So this is the velocity time graph. It starts at 0, but the ball is starting high up. And basically we're just going to look at each section a bit at a time and work out what's going on. So our first section here, the ball was dropped, so the velocity started at 0 up there. and then it increases in a negative direction. So the velocity is negative, it's sloping down the way, so the acceleration is negative, i.e. it's speeding up in a downward direction. So this is a ball falling. The next section between B and C, the velocity values are still negative, it's still below the axis, but the acceleration is positive. The line is sloping up the way. And because these have both got opposite signs, it's slowing down, but it's still negative velocities, so it's still downwards. Now, what's happening that's caused it to slow down? Well, the ball has hit the ground. And although we often think of that as instantaneous, and it's been exaggerated a wee bit, the length of time in this graph, what we've got there is a compression of the ball. So the ball has hit the ground and it's squashing down, and that's giving you this slowing down effect. So point C is when it stops squashing, it's when it changes from squashing down and the ball starts to expand again. So between C and D, the ball is expanding, so that's physically what's happening. What do we know at that point? Well, we know the velocity is positive, and because the line is sloping up the way, that the acceleration is positive as well. So what we've got is speeding up upwards. And like I say, physically what's happening there is the ball is bouncing back, basically. It's expanding again, having squashed when it hit the ground. Eventually it will leave contact with the ground, and that's why between B and D, that was when it was in contact with the ground, and that introduced other forces, so that's why the acceleration is dramatically different at that point. But D is when it leaves contact with the ground. If you notice the value there, right, it's leaving it about, say, plus 6.4, whereas it hit it at round about minus 8.8. So it has lost a wee bit of energy in the bounce, which is not surprising. That would happen in the real world. So the ball has now got some upwards velocity because of that expansion. So at this point, right, the ball is moving upwards, but it's no longer in contact with the ground, so its weight is going to slow it down, acceleration due to gravity. So the velocity is positive, but we're back to negative acceleration due to gravity. So it's still on the way up, but these two have got opposite signs, so it's slowing down upwards. It's slowing down and getting to zero. So point E is the highest point after the first bounce. So when the velocity changes from positive going up the way to negative going down the way. So its weight has slowed it down so much that it's now going to be moving back down the way. So this last section between E and F, we have got negative values of velocity, we're below the axis. The line is sloping down, so the acceleration is negative, i.e. we're back to the first section all over again, basically. It's speeding up downwards, and presumably F would hit the ground again, and this whole process could repeat.